Hi guys, in this video we would be solving a DSA problem which was recently asked in Google phone screen round. So in this problem we have an undirected and unweighted graph, okay? And all the nodes are nothing but English uppercase characters. And LS is represented by A, Bob is represented by B, and the destination is represented by D. So what problem is asking? The problem is asking that we have to return the minimum distinct edges from LS and Bob to destination D. I repeat, we have to find minimum distinct edges from LS and Bob to the destination D. I hope you understood this part. For example, let me show you. Let's say LS first goes to this F, then D. So the total minimum, the total distinct edges taken by LS is 2, okay, right? And the Bob first goes to this C, then E, then D. So the total distinct edges used by Bob is 3. So the answer is 5. So we have used, LS and Bob have used 5 distinct edges in order to reach destination D, okay? But there's one more point in this question, which is both can go in the same car using common edge after common node. Let me show you this with an example. So in this example, if LS and Bob both takes this path, so this would be the common node, right? Okay. So this edge is used by LS and Bob. Hence, it would be considered only once. We would not consider this edge 2 times. So this is what this particular point is saying. If any edge, if any edge is used by both LS and Bob, then that edge would be considered only once, right? So the minimum distinct edges for this test case would be 4. Let me show you how. LS first goes to C, Bob also goes to C, and they both goes in the same car. So all these edges would be considered only once. So 1 plus 1 plus 1 plus 1 is nothing but 4. I hope you understood this question. Now what you can do, you can pause the screen and try to solve this question on your own. Okay. So I hope you have tried this problem on your own. So in this problem, we saw that when LS uses individual path and Bob uses his own individual path, then the distinct edges were 5. And when both of them used a common node, then the distinct edges used were 4. Okay. Hence, what we have to do, we have to use the common node so that the answer would be as less as possible. Okay, we have to use common node in order to reach the destination D. Now there can be multiple common nodes. Like in this case, C is one of the common node, right? So also we can have something like this. There can be this Z node and Z is connected to A, C and B. So Z is also one of the common node. So if LS goes to Z and Bob also goes to Z, so total edges taken by both of them would be 2. Then they will travel, they will travel from Z to C, then C to E, then E to D. So total it would be 3 plus 2, which is 5. So point that I want to mention is there can be multiple common nodes and I have to find that common node which yields minimum distinct edges. Okay, I hope you understood this part. Now in this case we already know that C is the best common node because answer was the minimum, which was 4. How it is 4? Let's try to understand that part. how is the minimum distinct edges is 4. So observe one thing, from A we are reaching C. So total number of edges from A is 1 plus total number of edges from B to C is 1 plus total number of edges from C to D is 2, and this is why we are getting answer as 4. So the formula to get the minimum distinct edges is nothing but total edges from A to the common node plus total edges from B to the common node plus total number of edges from common node to D, right? But there is one fault in this formula, that is, let's say we have this graph. Okay, now C is the best common node, right? Now according to this formula, which path should I take? Should I take this path or this path? I don't know. I don't know which path we have to take according to this formula. We are just saying total number of edges from A to a common node. But in order to get the minimum distinct edges, we already know that this particular distance should be as minimum as possible. Hence, we know that we have to take this path. And what is this path? This is the minimum distance from A to C. Okay, this distance is nothing but the minimum distance of from A to C. So let me modify this equation. So the new equation becomes minimum edges from A to C plus minimum edges from B to C plus minimum edges from C to D, and this is what we have to find. I hope you understood this part. Okay, now observe one thing, we have to find minimum edges from a source to a destination, right? So when we see this kind of stuff like minimum from a source to a destination, then two algorithm comes into our mind. The first is BFS and the second is Dijkstra's. Okay, and the best approach to use over here would be BFS. Why? Because I think Dijkstra would be the overkill over here, because this graph is unweighted graph. So we can use BFS approach over here. Okay, so we are clear that we have to use BFS, and we also have the source, but we don't have the target or we don't have the destination. Like we just know that the destination would be the common node. Now common node can be anything, right? It can be X, it can be C, it can be Y, it can be anything. So what I'll do is I'll use the BFS from the source and I'll calculate the distance from source to all the nodes, like from A to X, from A to C, from A to F. And we know that BFS gives the minimum distance from source to any node by default. Okay, let me show you with an example over here. So let's say this is our new graph. Okay, LS is A, Bob is B, destination is D. So this first array represents minimum distance from A to any particular node. So for example, minimum distance from A to A would be 0. Minimum distance from A to B would be 2, right? Minimum distance to C would be 1, right? So basically this array represents the minimum distance from A to any particular node. How can we calculate this? Just use the BFS approach. Like start from this. So total distance covered till now would be 0. Then when your BFS goes over here, so automatically it will be 1, and for this also it would be 1. So when you reach at F, just put 1 over here, and for C also put 1 over here. Then BFS would move forward. So when you reach B, put 2, and similarly when you reach E, you also put 2. So this is how we can get the minimum distance from A to all the particular nodes. Same thing for B and the same thing for D. I hope you understood this part. Now in place of this common, we can put A, right? Then we'll put B, then C, and so on and so forth. So whichever one is the best common node will get us the minimum distinct edges, right? So this was the solution. Now let's move to the code. So in the code, we are using this particular test case, the first test case. And for this test case, we already know the answer would be 4. Okay. So we have the adjacency list over here, and I'm passing that adjacency list to this function, which will return us the minimum distinct edges if it is possible. Like it is not necessary that this graph is connected. Maybe we have A, D, and B is in the second component, right? So in that case, it is not possible. So in that case, we would return -1. Okay. So what we have done, we have called this BFS function, and the source is D, A, and B as discussed. We have called this BFS function 3 times and constructed that arrays. Okay. You can pause the screen and check out the BFS function because it is very trivial. Okay. And then we are just iterating through all the particular nodes, and we are trying to minimize the addition of all the 3 nodes. And if minimum distinct edges remains maximum, integer maximum, then we are returning -1. Else we are returning the minimum distinct edges. So in which case minimum distinct edges will remain -1. In the case where obviously from LS, let's say LS can reach destination and Bob cannot reach, or Bob can reach the destination and LS cannot reach, right? Something like this. So in that case, we are returning -1. So this was the code. And if you have any doubt in the explanation or the code, let me know in the comment. Thank you.